Hello everyone, this is the third part of our video, and in this video we're going to perform a Neumann stability analysis to show theoretically that the limit of stability on the explicit differencing scheme used in part 2 is 0.5. So in part 2 we used Python simulation to show that when the dt is r is greater than 0.5, it's not going to be stable anymore, right? Using the explicit differencing method. So in this video, we're going to try to use Neumann stability analysis to show it theoretically. Okay, so here I have the equations from the last part where we derived. So I'm going to just copy it, which is the temperature at a specific point at time is equal n plus 1. So this is an equation that represents the temperature of a specific point at t is equal to n plus 1 respect to other things. Okay, and we also know that our equation that we were using was alpha, the second derivative of time respect to x, right, was equal to the first derivative of time respect to so alpha times the second derivative of a temperature respect to x is equal to the first derivative of temperature respect to time, right? Okay, so what von Neumann said is, so he said that our temperature is equal to the e to the I kx times the e to the I k squared t, where x is, in our situation, j times delta x, and where t is n times delta t for our specific case, right? Okay, so let's try to use this idea, the idea of von Neumann, to apply to this equation up here. Okay, so we have tj, n, right? So let's derive everything. So that's going to be e to the I is where I is like square root of -1, imaginary number, k times, where k is the thermal constant conductivity, and k is the constant here, and x is going to be j times delta x, right? And e I k for t, that k squared, n times delta t. And we also have j, temperature at j minus 1 and n, that is going to be e to the I k j minus 1 delta x e to the I k squared n times delta t. And we also have temperature at j plus 1 at n, right? And that is gonna be e to the I k j plus 1 delta x e to the I k squared n delta t. And our temperature at j n plus 1 is going to be equal to e to the I k j, I forgot my mistake, so delta x here, delta x is here, e to the I k squared, it is, yep, n plus 1 delta t. Okay, so now can we express all of the terms in terms of t at j at time n? Okay, so this thing is going to be t j at n multiplied e to the negative I k delta x. right? If I open this, if I divide it into two powers, that's what I'm gonna have. So for this one, that's gonna be Tj at n times e to the ik delta x without a negative sign. And this thing is gonna be the temperature at Jn times e to the, so now it's respect to n, right? Ik squared delta t. So now I can plug in those back to this equation. Okay, I have R times J plus 1 at temperature at J plus 1 at times equal to N, which is this thing, right? Okay, I'm gonna write down R is equal to Tj N. Okay, let me factorize R. Okay, let me factorize Tj plus J and N. Okay, that's gonna be, and let's not touch this, okay? I'm gonna factorize Tjn out of the brackets, so for this part, that's gonna be R times e to the ik delta x, right? Minus 1 minus 2r Tjn, so I already factorized it, and Tj minus 1, that's gonna be I think I made a mistake here. So yes, when I was opening it, I forgot R here. So that's going to be the R here. So that's going to be e to the ik delta x, but with negative R. Let's put R here. Is equal to Tj at n plus 1. Let's gonna leave it as it is and not connect it to Tj at n. Okay, and so we know that e to the ix is equal to cosine of x plus I sine of x, and e to the negative ix is cosine of x plus this I'm negative I sine of x. So if I use these in my equation, I'm gonna have Tjn is equal to 2, so sines are gonna cancel out each other. I'm gonna have 2 cosines, so I 2 r cosine of k delta x minus 1 minus 2r is equal to Tj n plus 1, right? Yes. So so now I'm going to consider the thing I have in the middle. That should be balanced between negative 1 and 1. So if I factorize to r, I can write it down as 1 plus, I can write it down as 1 plus 2r cosine of k delta x minus 1. Okay, and now if I solve this inequality, if I subtract from both sides 1, that's going to be negative 2r cosine of k delta x minus 1 smaller than 0. Okay, so I have a cosine, right? So the cosine lies in between negative 1 and 1. So if I subtract 1 from a number which is equal or less than 1, I'm still going to have either 0 or a negative value, right? So this is going to be satisfied for all values of r, no matter what we do. So we don't have to consider that, but so we're going to do everything with this side only now. Okay, delta x minus 1. So this is, now I know this is a negative number, right? And if I divide the whole thing, okay, let's divide it by 2 first. So I'm gonna have negative 1 r cosine k delta x minus 1 and so the biggest number this can get is gonna be the negative, so the cosine k delta x minus 1 lies between, so the biggest number it can get is 0 and the smallest numbers it can get is negative 2. So we're trying to find the upper limit, right? So if we divide negative 1 to negative 2, the sign change, there's going to be the sign change, and we can find out this relationship. So the Neumann stability analysis now theoretically proves that if we use the explicit differencing method, our r is going to be restricted until to be smaller than 0.5. So this was the third part of our video, and in this video we proved that with Neumann stability analysis that r is always, for this method, r is always should be always less than 0.5. Thanks for your attention.